speaker, who is Sudeshna Boro Saikia, who's going to be telling us about Kappa Ceti. So please take it away.
Thanks, Victor. So hi, everyone. I am Sudeshna, as Victor said, and I am a postdoc here at the University of Vienna. So I'm going to talk about Kappa Ceti, and this is work that has been done in collaboration with a lot of people, and quite a lot of them are actually present here today. So, so the title, as you can see, is Evolution of Magnetic Activity in Young Suns. And if I can, yeah. So why young suns? So young suns are very interesting targets because of, if you look into the rotation versus age relationship, and if you look at the main sequence right after the disk is gone, then you see that the rotation rates of young sun-like stars are non-unique. In the very early stages, around the first few 100 million years, you see that stars either follow a slow rotation track, a medium, or a fast rotation track. And only later on, roughly around at 1 giga-year, or maybe slightly ahead, the stars actually do converge. And in this case, then you see the power law relationship between rotation and age. So this period is very interesting because you see there is a wide range of rotation rates you can see in young sun-like stars. And this period, which falls around a few 100 million years, is also very interesting also for planets as well, because this is during the time when oceans are forming on planets, specifically rocky planets, and you might be developing a secondary habitable atmosphere. So you want to know what kind of magnetic activity these stars have, because if you have a very, very slow rotating stars, then it means that the magnetic activity might also be much weaker. And in this case, the high energy radiation and winds from these stars might not be able to get rid of the primordial atmosphere. And then you're left with a gas giant. Or you might have a very fast rotating stars, which might be that you have very strong activity, and that might lead to a very stripped down atmosphere like Mars, for example. So in between those two cases is the sweet spot when you might develop a Earth-like habitable atmosphere. And for this, understanding how do the magnetic activity and in relation to that, the stellar magnetic field, winds, and high energy radiation of stars vary is quite important as well. So that's why I was focusing on, in this case, a particular young sun, which would be Kappa Ceti in this case. And Kappa Ceti has an age roughly around 600 to 700 million years. So it falls in the slow rotating track of sun-like stars. So, and we were interested in learning how does the magnetic activity and magnetic field of this star varies over time. And to understand its activity evolution, what we did was we took the chromospheric activity as a magnetic activity tracer. And it's very good to do this because we have a lot of data sets that actually do this monitoring. And in this case, what we do is we take that particular line, which is the calcium H and K lines, and we see that there is a strong emission in the line, and this emission is due to the magnetic heating of the chromosphere. And by measuring the flux in these emission lines and normalizing it, we can actually determine the activity level of a star. And this is what was done previously. And this is data set taken from the Mount Wilson survey, which was led by some of the papers down here, Baliunas et al. And Saran Baliunas. And what you see is that the star has a very variable activity, chromospheric activity. And in this case, you'll see what you see are the measurements from this Mount Wilson project in black. Then you have the mean level of activity by this dashed horizontal line. And then what I plot here is also the solar activity variation over a solar cycle, which is shown in this gray region here. And previously from the Baliunas paper and from the Saran Baliunas 1992, there was one strong activity cycle which was detected. And this one was around 6 years. And over multiple years, when you do a generalized Launce-Gargal periodogram, which we did in the 2018 paper, you see that you need the 6-year period together with a longer, around 22-year period to actually show the variation in the cycle. And this is what you see here, which is the red line, which the red curve basically shows a combination of the second 6-year period and the 22-year period. So it shows like this star has multiple cycle, which was not surprising because a lot of stars do show this very variable cyclic activity. So this is interesting for this star. And then, so these are the two chromospheric cycles. And then what we did is in recent years, this star has been monitored using multiple different programs, one of which will be the Lowell Observatory long-term monitoring of sunlight stars. And in recent years, also the Tigger telescope is also monitoring these stars as well. So what we did was we combined the Mount Wilson data set together with the Lowell and the Tigger data. And then we also had our own Narval observations as well, which did monitor these specific chromospheric lines. And that gives us a time baseline of around 50 years, which is great. And now what you see here are, again, the green data points are monthly averages from around late 1960s up to 2020. The error bars show the dispersion in these monthly averages. And the dotted vertical line shows, so anything on the left of this line is basically the older data set from Mount Wilson, and then the new ones are shown on the right of this line from around mid 1990s until now. And this blue dashed curve now shows the same 22 plus 6-year cycle from the Mount Wilson data set. And as you can see, this actually shows that this is in good agreement with what we see in the time series. So specifically in the middle of the time series, we have good agreement between these two cycle periods in the data. But of course, when you look at the very early stages and also during the later part of the time series, it's not necessarily a very good representation. It seems like there might be either multiple periodicities or maybe these cycle periods have changed over time or evolved over time. So what exactly is happening there? So because in the later half, we do not see such a good agreement with these previously known cycle periods, what we did was we only took the later half of the data set and we said, okay, now we have around 20 years of data. Again, do the same thing, take monthly averages, bin the data. Then this is roughly the dispersion in the data set. And then we did a generalized Lomskargel periodogram on this. And now when we do this periodic analysis, we see that there is a strong peak at around 3 years. And that is the dashed red line here. So as you can see in the later half of the time series, you only can recover the 3-year cycle period, which could be harmonic of the around 6-year cycle period. So it totally shows that, when you have a specific part of the time series, the periodogram can give you certain peaks might show up, which didn't happen in the previous one because the 3-year cycle was a bit harder to detect in the long time series. So we didn't recover it very well. But then the question is, even this cycle period is not necessarily in very good agreement because you do see a bit of a scatter here. So that's why we phase folded the data to see how exactly is the data set agreeing with this 3-year cycle period. And what you see here is the phase folded curve for a period of around 3 years. And then you see that there is a good bit of scatter here in the data set as well. So it shows that the 3-year cycle again, period is again probably has a bit more variability that cannot be explained just by the 3-year period itself. Now, with this kind of data sets, specifically since we have around 50 years of data, so the question was, can we actually do something better in terms of the period analysis, not just Lomskargel, but can we do something similar to a wavelength decomposition, for example? So the idea is that instead of just looking at the frequencies here, we also want to know in which time period these frequencies are occurring. So that's what wavelength decomposition does. So now when you do that, then you can get this this plot here, which shows the time axis on the x-axis, and it shows the periods that is recovered by this particular wavelength decomposition code. And what you see in the hatched area is basically shows the confidence region. So anything within that cross-hatched region is, you shouldn't trust it, but anything in the rest of the area, this is what we are going to take in the end of the day. So what you see here is that the wavelength decomposition actually does recover the periodic signals that we also saw in the generalized Lomskargel periodogram. So what we see here is around, we have a period which is around 6 years, which is shown by these darker, so the darker colors represent that there is a periodic signal present here. So you see this period, which is actually quite dominant in the middle part of the time series. Then in the beginning, we also see a time cycle period, which is roughly around 3 years or so. And later on in the time series, we also see this 3-year period picking up. So it does seem like that indeed what we saw in that there were multiple periodicities in the periodogram data, in the periodic analysis. It's also seen in this wavelet analysis as well. So that was very encouraging, but also at the same time, it's also interesting because you see that this cycle period does appear or disappear during the time series as well. So what is actually happening? Are these two chromospheric cycles, or is it just one cycle that evolves and changes its length over time? So what exactly is going on here? So it's quite hard to constrain this just by looking at chromospheric activity. But then also we want to know what exactly is the magnetic cycle of the star, considering we do see chromospheric cycles. So for that, we actually use Zeeman Doppler imaging. So this star is known to have magnetic surface magnetic field strength of around 500 Gauss, which was done using the Zeeman broadening method. And if you do the Zeeman Doppler imaging, which was done already by Lisa Rosen and Donna Cimento, where they detect a large scale magnetic field of around 20 Gauss. So this is substantial field strength. And this is basically how Zeeman Doppler imaging map would look like for the star for this particular epoch, 2012. And what you see here are the radial, the azimuthal, and the meridional field. And in the radial field, you see a positively dominant positive magnetic field region, which is in the upper hemispheres. And in the azimuthal field, you also see a negative magnetic field, which is more or less dominating around the equatorial regions. So you do see this simple but one single polarity dominant magnetic field in 2012, which was the first data set that was actually used by Rosen and Donna Cimento. Now, since then, we have carried out multi-epoch measurements, and we have a total of 6 epochs of spectropolarimetric measurements of this star. And then I'm just going to show you just the radial field and show what we actually recover for this star. So if you now take just the radial field, then you see at first, these are the 3 epochs that were spread around over multiple years. We do not have a very high cadence. Here you see the dominantly radial field, and in 2013 you see that the field is getting a bit more complex. You see some stronger negative areas as well, and then in 2016 also you see this slightly bipolar kind of regions. So strong both polarities are present in the upper hemisphere, and just to remind you that these data sets were taken quite far apart. So unfortunately, we do not know how the magnetic geometry looked like in between. But recently we did take some additional measurements, and this time we actually did measure the magnetic field of the star over a slightly higher cadence. So since 2016, we have one in 2017, and here we see that the magnetic field is now negative in the upper hemispheres, and then later on in 2018, it does rapidly evolve from a dominantly negative field to sort of a mixed polarity to potentially a single polarity magnetic field again. And it shows that since 2012 to 2018, we did appears that the magnetic field, the radial magnetic field, changed polarity from positive to negative, and then from negative back to positive. But then the question is, how exactly is this polarity reversal happening in comparison activities? Back to minimum in 27. In terms of the activity cycle itself, so what I plot here is at first the 3-year cycle period, which is over here. And then you have the radial field and azimuthal field. So in the top, what you see is that every time you have a dominant positive polarity in the radial field, then I show it as a red bar, and the slightly faded colors represent that, okay, there is a positive magnetic field, but I also see a slightly increasing negative field as well. And now in this case, you see that indeed in 2018, the star was at minimum activity, but when you go back to the change in polarity of the radial field, you see that the polarity change happens not at the minimum, but actually very close to the maximum. So which is not something that we see in the sun. And this is something that you also see in the azimuthal field as well, because you see this negative polarity in 2012, and then later on, it changes polarity together with the radial field, but this time it's not next to the magnetic, next to the activity cycle maximum. So this is kind of strange, because in the sun, we do expect it to happen around minimum. So the first thought that might be that indeed, it might be that the chromospheric cycle is much smaller, considering what we see in Tabu as well, because it happens, the magnetic dipole, the magnetic field flips its polarities on a very shorter time scale. So is this what is happening in Kappa Ceti or not? So that's something that definitely needs further high cadence observations, because we do see that in the few later epochs where we do have high cadence observations, we do see the magnetic field rapidly evolving as well. So at this point, I would just say that Kappa Ceti has two prominent chromospheric cycles, and its magnetic field geometry does reverse polarity, but it's not necessarily a solar-like polarity reversal in comparison how the activity cycle and magnetic cycle are in good agreement. So we do not see this good agreement in Kappa Ceti. And one thing that I should also point out is that this is something that is also recently seen in the case of Epsilon Eridani, which is another young, slowly rotating star. So if this indeed is a true representation that, these kind of stars do not necessarily show a solar-like evolution of the magnetic field in relation with the chromospheric cycle, then is it something that we are seeing that, that these stars have probably stronger surface effects, which might lead to the appearance of multiple cycles, or is it what we are seeing here? So to confirm or deny these things, I think we need longer high cadence observations to see what exactly is happening, not in just terms of magnetic field reversals, but also what's happening in the chromospheric activity as well. So yeah, so with that, I think I'll just wrap up. So maybe I have more questions than answers, but it would be very nice to see what you think about this as well.
Thank you, Sudeshna, for all that talk. So if anyone has any questions, but maybe I'll ask one quickly. Are there any plans for any more observations with Ceti?
There are a few observations that I have. I think one epoch from last winter, but I still need to look at it. And as it's new on Arval, I don't know actually what the situation is with the normalization, so I have to check it.
Okay, sure. I saw that Lisa had a question, and I might be able to guess what it is, given the talk she gave earlier.
Hello, hey Sudeshna, very nice talk. Very interesting target.
Yeah.
As you probably guess, have you checked maybe the fraction of the axisymmetric field? As I saw on the radio field, it should vary a lot.
Yeah, it does vary, but not necessarily with any cycle. So okay. There is no cyclic behavior in that. But to be honest, there is not enough data points as well. So 6 observations only. So then that's also spread out over multiple cycles. So it's hard to tell, I would say.
Okay, so let's finger crossed for more observations.
Yeah, indeed. Yeah.
Thank you.
And a question from Thomas Ackman.
Thanks for a nice talk. I'm wondering if we will be looking at the sun, at what point would we see the change of the magnetic field, because it happens on different latitudes at different stages. So at higher latitudes, it happens in the middle of the when the sun is at its most active point, and later at lower latitudes, it happens when its activity is low. So I don't know. Maybe Lisa also could comment on that thing. That what would we see actually in the sun? with Zeeman Doppler imaging?
Just from my experience with working with, say, for example, 61 sig A, where we do see a very good agreement, not just in chromospheric and the Zeeman Doppler imaging, but also with coronal activity as well. So what we see here is that at maximum, because of the appearance of strong active regions, you do see a complex magnetic field at maximum. And this is what I was expecting. If it is indeed the chromospheric activity maximum of the star, then I was expecting not a polarity flip, but also a stronger complex field, or maybe even a weaker complexity, but a complexity that I was looking for. But at the same time, as you said, even in the sun, you do, as Lisa also said, you have this prolonged, in certain cases, a prolonged minimum or a prolonged period of non-appearance of very strong active regions. So it might be also that instead of just having this very clear-cut 3-year cycle period, this from 2017 to 2018, we might be seeing something of something at some sort of a valley of minimum, where 2017 is probably just before the actual minima and 2018 is just after the minimum has hit. So yeah, so it depends on how you interpret this. And without high cadence observations, I think it's hard to pinpoint exactly what is happening here. Maybe Lisa has something to say on that.
Yeah, I would also just add, it could be really just bad luck, as we saw that even for the sun, there's quite a large spread in the field topology we see, especially during the maximum. It can quite vary a lot.
Yeah, exactly. I'm also thinking if that strong negative polarity, or not strong, is still the field is not that strong, but it's still dominantly negative polarity. And the question is whether we are seeing this because there are stronger negative regions and that's canceling it out and we just see a net negative field, or is it because it just you don't see any active regions? So that's another question altogether. All right.
Are there any other questions?
I have a very short, I always have short questions. Sorry, I give it up. No, it's not a short question anymore. So thanks for the nice talk. I am a bit doubtful about this S-index periodicities. Maybe I missed something, but can you please go back to the maybe in the wavelet. Actually, here, for instance, in the wavelet, we do see some indication of a prolonged period at long period one, like 8 years also.
This is around 6 years.
Yeah, 6. Okay, but you're getting too close to the edge of the reliability boundary, right?
Yeah.
I mean, so maybe this is actually always the case, but it ceases because of the other signal, or because we are losing our competence near the edge, like in 2010 and later. So it's
you mean this particular bit, right?
Well, actually, also the long period case. So we cannot easily say here that the long period ceases and the other starts, because we are getting
of course,
close to
true. Yeah, you're true there. Yeah, that's why I'm a bit skeptical in saying that. For example, if I go here, I only plot the 3-year, but doesn't necessarily mean that that's the only cycle period there. But just not to overcrowd the plot, I plotted this. But even when you actually do take the longer period, it still doesn't agree with the minimum and maximum. This polarity flips do not necessarily agree. So I have another plot that shows that as well, but I didn't show it for with the 6-year period. But the point is that no matter which one you take, it doesn't necessarily go with the same sunlight view of negative polarity flips to positive and then back to negative in cycle minimums, right? So that doesn't happen in this chart, whether you take the 3 or the 6-year period.
One should also note that I think, well, what you think about is the flux emergence. As you go to high activity stars and fast rotating stars, the evolution of magnetic flux at the surface might affect these periodicities a lot more than in the sun. in which you don't see an active region over many rotations and so on. So I think these short periods in the S index are rather doubtful, aren't they? What do you think? I mean, especially in regards to the possibility that what we are seeing is actually the flux emergence signals.
Yeah, that's true. I mean, considering we also have large, potentially larger spot coverage in these stars as well. And the question is it just a surface effect that we are detecting, or is it something that based on the inclination of the star, you also have some asymmetry in the northern and the southern hemisphere, if that's what's producing these kind of signals in the chromospheric activity as well, right? So those are additional questions on why we see these short period cycles. So that's why I think if you compare these two, then of course you do see two chromospheric cycles, but whether which cycle is the actual like sunspot related cycle or a dynamo related cycle, it's very hard to tell. And if you now look at the magnetic field reversals, then it complicates the matter even further. So indeed, you cannot be absolutely sure which exactly is the actual cycle period. But this does show us the complexity of the problem, how with just these measurements, it's very hard to say which indeed is the true cycle, dynamo cycle period of the star, for example. So
yeah, thanks a lot. Yeah, I agree with you. Yeah.
Okay, so thanks for that, Sudeshna. We